Hello everyone, welcome to our last installment of Chapter 16. This is where we will continue our discussion of finding the pH of salt solutions. And in this example, we are going to work through species containing salts that contain amphoteric or amphiprotic species. Okay, so our first example is, do you expect a solution of magnesium bicarbonate to be acidic, basic, or neutral? And so this is magnesium bicarbonate. Okay, so at this point you should probably have a sense of the process that we are using. So our first step is to dissolve the salt in water. And since it is an ionic species, it breaks up into its ions. Our second step is to investigate how the cation reacts with water. So magnesium 2 plus water. This magnesium is an acid, but it has no proton to be able to gain, which means that it has to take the hydroxide from water, giving us MgOH2 plus H3O plus. This magnesium hydroxide is a strong base, and so we know that this reaction of magnesium plus water does not occur, because as soon as any strong base forms, it immediately dissociates again. And so our magnesium contribution is neutral. There is the Ka of this expression does not exist. Okay, so now we need to consider the anion and how the anion reacts with water. So I have HCO3 minus plus water forms an equilibrium. Now, remember that the first thing that we have to do is ask if this is an acid or a base. It turns out that we have a proton and we have an anion. And so this, oops, that's not what I wanted to write, is both. And so I'm going to change color here so that we can mark these out as our acid reaction, where HCO3 minus plus water behaves as an acid. So the base takes the proton, forms an equilibrium with H3O plus CO3 2 minus. And we also have the base reaction, HCO3 minus plus water. This minus charge takes the proton, giving us OH minus plus H2CO3. So now we have a species that is behaving as both an acid and a base. And so what we want to do is we want to find the Ka expression for the acid. And this is going to be something that we can read directly off of the table, because carbonic acid is an acid. But remember that this is carbonic acid losing its second proton, And so that means that Ka is equal to Ka2, which is 4.7 times 10 to the minus 11. We also will need to find the Kb of this reaction, which is going to be equal to Kw over Ka1. And it's Ka1 because it has the fully protonated species and the singly deprotonated species in solution, and this is the same reaction as is described by Ka1. So I have 1 times 10 to the minus 14 divided by 4.5 times 10 to the minus 7. And this is equal to 2.22 times 10 to the minus 8. Okay, so now step 4, I have to put all of this together. My magnesium behaves as a neutral. My bicarbonate behaves as both. And so just like we did whenever we had a weak acid and a weak base in solution, we have to determine which one wins. And so in this case, my Kb is greater than my Ka, which means that the bicarbonate is going to behave as a base. So for this overall solution, I have a neutral plus a base, means that the solution will be basic. Okay, so in the next slides, I'm going to walk through the same example in a typed up way, just so you hear it again and you can see it more neatly. Okay, so my first step was to break things up into its ions. My second step is to look at the cation, and we see that the cation reaction with water forms a strong base, which means that that cation behaves as a neutral ion. I then, in step 3, I look at how the anion reacts. And the anion reacts both as a base and as an acid. And so I calculate out the Kb for the base reaction and the Ka for the acid reaction, and I find that the Kb is greater than the Ka, and so the bicarbonate is behaving as a base. I then, in step 4, I put it all together. And so magnesium's behaving as a neutral, my bicarbonate is behaving as a base, and a neutral plus a base is going to result in a basic solution. Okay, so now I'm going to walk through another example of this type. Okay, so for our next example, we have, do we expect a solution of potassium dihydrogen phosphate to be acidic, basic, or neutral? Okay, so step 1, I take my potassium dihydrogen phosphate, I dissolve it into water, and I get potassium and dihydrogen phosphate. For my second step, I look at how the cation reacts with water. And there's no proton in the cation for it to be an acid, so I know that it has to just take the hydroxide. But my KOH, this is a strong base, which means that my cation is a neutral ion. Step 3, I need to see how the dihydrogen phosphate behaves in water. And I need to change color. So I'm going to look at the H2PO4 minus in water. And I'm going to look, this is amphoteric or amphiprotic. And so I'm going to first describe it as its acid reaction. And so that means that the water is the base taking the proton, giving me HPO4 2 minus plus H3O plus. And I also need to look at this as a base where H2PO4 minus plus water. The base takes the proton, giving me H3PO4 plus OH minus. So now I need to figure out, since this dihydrogen phosphate is both an acid and a base, I need to figure out which one wins. And so to do that, I need to find the Ka of the acid reaction. And this means that I have to use my table and look up phosphoric acid. And this is going to be described by Ka2 because this is the phosphoric acid losing its second proton. And Ka2 for phosphoric acid is 6.3 times 10 to the minus 8. I also need to look up the Kb for the base reaction, which is going to be Kw over Ka1. And it's Ka1 because I'm working with the fully protonated species and the singly deprotonated species, which is going to be 1 times 10 to the minus 14 divided by Ka1 for phosphoric acid is 7.2 times 10 to the minus 3. And so the Kb is 1.39 times 10 to the minus 12. So step 4, I have to put it together. My potassium is neutral. My H2PO4 minus is both, but it is going to be acidic because the Ka is greater than the Kb. A neutral, that's not how you spell neutral. Sorry guys. Neutral plus an acid is going to result in an acidic solution. Okay, so on the next slides, I'm going to walk through this more quickly in a typed up way so you can see it nice and neatly. Okay, so my first step was to dissolve the salt into water, breaking it up into its ions. In my second step, I looked at how the cation reacted with water, and I found that it produced a strong base, which means that there is no reaction from the cation, and so the potassium is neutral. I then look at, in step 3, I look at how the anion reacts, and I see that the anion is amphiprotic because it has a proton and a negative sign. So the negative sign makes it behave as a base. The proton makes it behave as an acid. And so I get both a Kb reaction and a Ka reaction. Using my table, I calculate my Kb. I find my Ka. And remember that this Ka is described by Ka2 because I'm going from diprotic to monoprotic. And I find that the Ka is greater than the Kb, and so the dihydrogen phosphate behaves as an acid. So then step 4, I have to put it all together. My potassium is neutral. My dihydrogen phosphate is an acid. A neutral plus an acid results in an overall acidic solution, so I expect the pH to be less than 7. Okay, that is it for chapter 16. Please continue to ask questions, post on discussion boards, reach out to me, attend our virtual office hours, talk to our TAs, read the book, work problems. Let me know what other tools you could use. Stay in communication with me. But now, if you've watched all of the Chapter 16 videos, you are prepared to begin working on the Chapter 16 practice problems, the Chapter 16 practice exam, and the other Chapter 16 materials that I have posted onto World Class. Know that I will now begin posting Chapter 17 videos, but you need to have Chapter 16 pretty thoroughly understood before we can move into Chapter 17. So stay in communication, stay healthy, get some rest, and I will see you in Chapter 17.